Qué barbaridad. Chicos, sí están de a poco, pero van viniendo los chicos. Buenas noches, jóvenes, con cada uno de ustedes. Gracias a Dios ya tenemos una mejor voz y podemos compartir de manera un poco más clara. Vamos a esperar que se encienda la cámara. Para que se encienda la cámara de mi lado. Mm, Vamos a ver. Muy bien, jóvenes, gracias por venir. Que ustedes que están viniendo a tiempo. Gracias a Dios tengo una mejor voz. Ah, Quería comentarles que la grabación del día martes, por obvias razones, no la subí. Está archivada, pero no la subí porque pues, me di cuenta que la voz era tan terrible que, la verdad, quien sea que quisiera reproducir eso, no se hubiera escuchado realmente, no sé si hubiera sido realmente de utilidad. Están las diapositivas subidas en el aula virtual, así que las pueden ver cuando deseen. Van a tener ustedes, en cuanto a grabaciones, lo del tema de intercambiadores de calor, las primeras 2 horas de la semana pasada y la de hoy, Dios mediante, ¿no? No la del día martes por el tema de la voz. Entonces esa no va a estar disponible porque en realidad no creo que hubiese sido tampoco de mucha ayuda. La voz era tan terrible que no creo que hubiera sido de mucha ayuda aun cuando lo hubiese subido. Eso es jóvenes. Entonces, vamos a revisar lo que tenemos eh, hoy que cumplir. Veamos. Eh, Veamos dónde se encuentra nuestro sílabo. Si no lo encontramos aquí, lo podemos buscar. Diseño de plantas. Tenemos nuestro sílabo número 14, la revisión 14. Muy bien, aquí lo tenemos. Vamos a proceder. El sílabo. Ok. Este es nuestro sílabo y podemos ver que hasta ahora se ha avanzado. Se puede decir, ah, mire usted, o sea, nos hemos pasado un día con el tema de intercambiadores de calor. Eso es porque no tuvimos un día clases. Es decir, hoy nos toca terminar intercambiadores de calor, inmediatamente movernos a unidades de separación. Entonces queremos aprovechar el tiempo en eso. Vamos al tema de intercambiadores. Correcto. Perdón, compartir que se encuentra aquí, intercambiadores. Muy bien, espero que todos puedan observar esto. Nos quedamos nosotros en el ejercicio 3, example 13.3. This is from Peter Stimmerhouse and West, Plant Design and Economics for Chemical Engineering. It's a good book. It seems this is the last edition of Mr. Peters. I don't know if they are alive or no. But at the time when I was a student, this is the book we used, yeah, and still we consider it a good book. Okay. So this is the example. This is what it says. Let's move this around. It says a horizontal shell and tube heat exchanger. Sometimes I will mention heat exchanger as just exchanger, but that's what I mean. A heat exchanger or an exchanger, we mean the same equipment. It's just a short for heat exchanger. So a horizontal shell and tube heat exchanger with 2 tube passes and 1 shell pass is being used to heat 9 kilograms per second of a 100% ethanol. That would be flow from 15 to 65 Celsius at atmospheric pressure. The ethanol passes through the inside of the tubes, and saturated steam at 110 Celsius condenses on the shell side of the tubes. The tubes are steel with outside diameter of 0.019 meters and a Birmingham wire gauge, that's BWG, Birmingham wire gauge of 14. The exchanger contains a total of 100 tubes, 50 tubes per pass. The ratio of total inside tube cross-sectional area per pass to header cross-sectional area per pass is, that is SI, that will be the ratio of the area inside of the tubes to the area of the header, that is area of the tubes to area of the header, can be assumed to be 0.5. The film coefficient for ethanol, estimate the film coefficient for the ethanol will be the ethanol fluid, ethanol flow, the pressure drop due to friction due to the through the tube side of the exchanger, delta PI. Okay, so they're requesting, or they are requiring we calculate the internal, they call it film coefficient, that is, film coefficient will be equivalent to the we will have the units in watt per square meter per Kelvin. That is heat transfer coefficient. They just call it film coefficient sometimes, but they are referring to the heat transfer coefficient. Okay, so we're seeing the Birmingham wire gauge. This is table 20.4. We see that for a 3/4 of an inch BWG 14, it's checking here, it says BWG of 14 and outside diameter of 0.019. So that will correspond, this is the outside diameter, 19 millimeters divided by 1,000, that would be 0.019 meters. But this is 3/4 of an inch. Then we have here, this will be the 2.108, that will be the thickness of the wall. And this will be the inside diameter, 14.834. Very good. So these are the dimensions of the tube. Also, it is saying that this ethanol, which is an organic fluid, is being heated with steam, saturated steam at 110 Celsius. So for light organics, we have a fouling coefficient. It goes from 1 times 10 to the negative 4 to 2 times 10 to the negative 4. You can see the units in here. This is all from Peter's book, chapter 14, by the way. This is a 2002 edition, the last edition of the book. So you could see that the fouling coefficient is between these numbers with the inverted set of units. So this is square meters, Kelvin, divided by watts. When you invert this, you will have 5,000 watts per square meter Kelvin. That will be the fouling coefficient. This will be the film coefficient. It says B, there is B in here. Coefficient based on clean surface. So this is B, and we have HD. Okay, so the coefficient for light organisms will be 1.5, between 1.5 times 10 to the 3 to 2 times 10 to the 3. Okay. It also mentions these goods for light hydrocarbons, like alcohols, ketones, that have a viscosity less than 0.5 times 10 to the negative 1 pascals per second. Very low viscosity. Okay, fluid conditions. For the side of the steam, checking here, do they mention anything about the pressure of the steam? They just mentioned that saturated steam condenses at 110. So it will be slightly over one bar of atmospheric pressure. 1 bar is 100 kilopascals. We don't have in the table a value for 110 kilopascals. But between 100 kilopascals or 100,000 pascals and 1 million pascals, we have these two set of this range of values. Since it is approximated by the value of 100 kilopascals, we may stick with this number that is between 10,000 and 15,000 watt per square meter Kelvin. So that will be the film coefficient that we could assume is directly from the table for the case of steam. Why do we need all these coefficients? Because we're going to use the formula to calculate the overall heat transfer coefficient, which is going to include the film coefficient for ethanol, it's going to include the film coefficient for steam, it's going to include the fouling coefficient for ethanol and the fouling coefficient for steam. And then hopefully we can obtain an overall heat transfer, internal overall heat transfer coefficient, considering both fluids. You can also see that for the case of steam, the fouling resistance will be between 0, that you can assume 0 for steam. There is no deposition on the side of steam because steam is usually just boiled soft water. That is water where magnesium ions, calcium ions have been removed. So you have water with no magnesium, no calcium, so that will produce no deposition. Remember that in an exchanger, you are boiling water. So when you heat up hard water, water that contains calcium, water that contains magnesium, that will deposit on the inside of the walls of the tube, or on the outside, whichever route the fluid is going. It will deposit if the water is hard when you heat up or when you boil the fluid. In the case of steam, because steam is just soft water being boiled in an exchanger, which is a boiler, soft water. That soft water will produce no deposition when you boil it. So you could also consider 0 for the fouling coefficient. But they left a range in this table between 0, 1 times 10 to the negative 4. So that would be a range. You know, you could consider it in case we specify that there is a fouling coefficient for steam. We could specify, but if you leave it at 0, then you will not be too far from the truth, because that's what happens. And because steam is usually is hard water that has been processed. So now what goes into the boiler is soft water. So you will not be too far from the truth if you just consider 0. Okay, now since they were requesting the film coefficient for this situation, for the heating of ethanol, there's a heat transfer coefficient, the film coefficient. We can use a correlation. That is, we can use the correlations that we have seen, the Cedar and Tate, the Ditus and Boulder, and there are many more correlations. These are just a summary of correlations. For example, this correlation of equation 1418, that seems to be very similar to the Cedar and Tate correlation we have seen before. We also see that, well, there is a small mistake in here. Instead of being 0.23, is actually 0.023. That will be the actual value here. Equations 1418 and 1423. This is for the pressure drop. You see delta PI, that's for the pressure drop inside of the tubes. And HI is for the film coefficient inside of the tubes. Equation 1418 and 1423 can be used to determine the heat transfer coefficient and pressure drop inside the tubes, respectively. Now that the average wall temperature will need to be evaluated to determine the effect of viscosity on the heat transfer coefficient. Very good. Now, this can be accomplished with a simple estimate based on the thermal resistances in the films associated with ethanol and condensing steam. So for turbulent flow above the transition region, that is when G is just M, the mass flow rate divided by the area, you might remember that, inside of the tubes. VI is the internal diameter inside of the tubes, and mu is the viscosity of the flow that goes inside of the tubes. When this ratio is above 10,000, when the Prandtl number is between 0.7 and 160, and when L over DI, the ratio of the length over the diameter is above 10, then this equation 1418 could be used. Once again, it's 0.023 instead of 0.23. And you might remember the mass flow rate, the density, there is velocity over viscosity is a Reynolds number. Here we have the Prandtl number, and this is the ratio of viscosity, the bulk viscosity to viscosity of at the wall, you know, and these are the different parts. This is very similar to the Steiner-Tate correlation that we have seen in last class. I think we saw that. Okay, so the property data. Please be aware that if ethanol came in at 15 and left at 65, so when we're going to look for the properties, we have to look for the average temperature of the bulk of the fluid. That is, if the fluid came in at 15 and the fluid left at 65, we have to make an average between the entering temperature and the exit temperature, so as to avoid having an error if we're too close. That is, if the temperature of the bulk of the fluid is around the average between the incoming and exit temperatures. If we take the incoming temperature, you know, and search for the different values of the parameters at the incoming temperature, when we do our calculation for the film coefficient, we might actually have an error. Our error will be perhaps considerable. So it is wise and it is recommended, and that's what the book practices, to actually make an average of the film coefficient, an average. In this case, since it came in, the alcohol, that is ethanol, came in at 15 and left at 65, the correct temperature to search for the value of the different parameters, that is viscosity, thermal conductivity, heat capacity, density, and thermal conductivity at the wall for steel, that will be the average temperature of fluid, as you see right there. So all the parameters at the average temperature of the fluid inside the tube. I think we have Puerto Limpio. Puerto Limpio está aquí afuera. Esperemos que no demore mucho. Espero que me puedan escuchar. Okay, the exchanger configuration. According to the problem, the outside diameter of the tube was 0.019. It was a Birmingham wire gauge 14. You might remember that. Birmingham wire gauge 14 had a thickness, a specific thickness of the tube, and it had an internal diameter. We can check that really quick, which will be in this table. Remember table 20.4? This is table 20.4 from Turton, although example 14.3 is actually from Peters. So, but that's okay, because this data is universal, whether it is published by Turton, by Smith, by Peters, by Gavin Towler, by any other book of plant design. The table is universal. So these values are true no matter what book they are in. Let's just move ourselves around a bit. So if we see here, this is the outside diameter, which is 19.05. The thickness, 2.11 almost. And the inside diameter is 14.83. So if we divide by 1,000, we will have 0.019, the outside diameter. We will have, what will this be? 2 divided by 1,000 is at 0.00, if I'm correct. Let me see, 2.1 divided by 1,000. Yeah, 0.0021, that will be the correct number in meters in here. And here will be 0.0148 or 0.015, whichever you want to consider. And here it will be 0.019. If we go back to our exercise right there, outside diameter is 0.019, inside diameter is 0.015, just like we saw. The thickness of the wall, tube wall thickness, 0.002, just like we saw. The area, the cross-sectional area, if I'm correct, is also listed in here. Let's see, thickness. Okay, so we don't have the area in here. But the area will be what is that? Inside diameter, we can divide that by 2. It's a 14.834. We divide by 2, so we have the ratio, and then we square that times pi. So it says in here, according to this calculator, is 0.0001728 or 0.000173 square meters. We come back here, 0.000177 it says in here, but I have 173 or something like that square meters. Okay, so the inside surface area of the tube would be 0.047 square meters per meter of tube length. That is pi times the divided by the length of the tube. So what does this mean? That means that what you consider for heat exchange is a wetted surface. That is the wetted surface, the area that is wet. Inside of the tube, the area that is wet, of course, the whole tube is wet. But for the heat exchange purposes, what matters is the surfaces where the heat exchanges, let's say, exchanges energy from one side to the other. Usually it is from the hot side to the cold side. So that takes place through a specific surface area, which we call wet area. The different books call the wet area. Wet area is pi times d, that is a circumference of the pipe, times the length of the tube, that is a wet area. That's why you see pi times d, and then we have to multiply times the tube length, and that will be in square meters, because pi times d is just linear meters times the tube length, and that will give us square meters. Hopefully this is understandable. That's a inside surface area. I should put here square meters. Okay. First, determine the mass velocity. The mass velocity is the flow rate divided by the cross-sectional area. That is the velocity inside of the tube. That will be, the units are kilograms per meter square per second. The Reynolds number, you guys might remember the Reynolds number. When you use G, that is the mass flow rate divided by the area, expression in the Reynolds number, then the Reynolds number would be expressed as this, as internal diameter G divided by mu, instead of internal diameter density velocity divided by viscosity. Prandtl number, this is the definition, the well-known definition, Cp mu over K. So these are the values. So we know from here that this is a turbulent flow, and this is a Prandtl number. You know, Prandtl number for a low viscosity fluid is 1.7, is very low. But in here it's not that low, it's 14. So there is some viscosity in here. So it seems, and sure enough, the fluid is not water, the fluid is ethanol. So there is some viscosity in there, it seems, because of the Prandtl number. Now, question 1418 for evaluation of the average heat transfer coefficient applies under these conditions. The only remaining unknown is in the relation is mu sub W, that is the viscosity at the wall. And this requires the temperature of the tube wall. So as a first approximation, we can assume the following. Since this value has not been given to us, what is the temperature at the wall of the tube? So in this case, the author approximates that possible temperature of the wall. So we can obtain mu of ethanol at that approximate temperature and then carry on with the calculations. So it was assumed, a couple of possibilities in here. It was assumed that the delta T across the ethanol film, that is from 15 to 65, that is, which made an average of 40, let's say, as if the entire tube was at 40 degrees, you know, between 65 and 15 divided by 2, that is 40. As if then all the tubes had a constant temperature, the inside temperature of ethanol across the tube was 40. And then outside of the tube, we had condensing steam of 110. So that difference between 110 and 40 of the organic fluid of ethanol, some percentage of that, it was assumed, that came from the increasing temperature of the ethanol film. So that between 110 and 40, 70% of that was absorbed by the ethanol film and caused the increase from 15 to 65. 70% of that increase in temperature between 110 and 40 it was responsible for the increase in temperature of ethanol. And it also says that 10%, both of these are just assumptions. And it also says that 10% of the difference between 110 and 40 of that increase in temperature was caused by the steam itself, which will be what is 70 degrees Celsius times 10% is 7. 70 degrees Celsius times 70% is 49. So if the temperature of the bulk of the fluid is at 40, and 70% of that difference will be absorbed, will be absorbed by the fluid. Remember, the fluid came at 15 and left at 65. So it could be wise to consider that the temperature of the wall has to be high enough for that heat exchange. So we have assumed, so if it's 70% of this difference, it will be 49 plus a 40 at which the average bulk temperature of ethanol is actually at. It was considered that the temperature at the wall was actually 89. And that makes sense because it has to be substantially high to take a fluid from a cold temperature like 15 and take it all the way to 65. So that makes sense. It has to be high enough to do that. But this assumption is going to be checked. So what you see in blue is assumption that was considered 70% of the difference between condensing steam and the bulk average temperature of the fluid. And that was added to the bulk average temperature of the fluid, and it ended up being 89. So at that temperature, we could search out for the property, the viscosity of ethanol in pascals per second. It came out to be 0.0004. Now, this ratio of viscosities could be calculated from that, Sider and Tate equation. It came out to be 2.25. So now, replacing all the numbers, remember, Reynolds number was calculated, and it was in terms of the GI parameter. The Prandtl number was calculated. The ratio of viscosities was calculated. So what else? K, DI, they are all known values, and they are part of the Nusselt number, actually. So to obtain the film coefficient, you have to multiply times the thermal conductivity and divide by the internal diameter. So you can solve for the film coefficient and obtain a value for that. So replacing the parameters that are already known, it came out to be 1,650 watt per square meter Kelvin. Now we have to check for the assumption. That is, check if this assumption, assuming that the temperature of the wall was 70% the difference between condensing steam and the bulk temperature of the organic fluid of ethanol, the bulk temperature of the bulk average temperature of the organic fluid, so that it was added to the bulk organic temperature, the bulk average temperature of the organic fluid, it came out to be 89. So that will need to be checked if that is correct. That is actually done in here. No fouling coefficient will be used for steam, just like mentioned. That is a good assumption because steam comes from soft water, so you can assume there will be no deposition on the steam side, and that would be a good assumption. You will not be far from the truth. That's what actually happens in real life, because you actually boil soft water, you don't boil hard water. Otherwise, the whole exchanger will be, or the whole boiler will be clogged in no time. The whole thing will be clogged in no time, and maintenance will be a disaster. Okay, now we have to check from table 14.3 a fouling coefficient of 5,000 watt per square meter Kelvin is adequate for ethanol. Let's check if that is true. We coming here, this is table 14, actually is table 14.3 from Peters. So for light organics, and ethanol is a light organic liquid, correct? So the film coefficient will be between 1.5 times 10 to the third, which is 1500, and 2 times 10 to the third, which is 2000. It will be somewhat between these two. But the fouling coefficient will be between 1 times 10 to the negative 4 and 2 times 10 to the negative 4. So when the units in here are square meters Kelvin divided by watt, so they are inverted. Units are inverted to the film coefficient units. So when we invert this, it comes out to be 5,000 watt per square meter Kelvin. That is a number that is going to be used here, as you see in there, as a fouling coefficient for ethanol. A no fouling coefficient will be used for steam. Now, this equation can be used to calculate the overall internal heat transfer coefficient. It will be the right equation to consider. And it says in here from table 14.4, the steam film coefficient can be estimated conservatively as 1 times 10 to the fourth. Once again, we can check this really quick. We can come in here, table 14.4, steam condensation at 100 kilopascals, I'm sorry. This will be the film coefficient in watt per square meter Kelvin. And sure enough, you see that it's between 1 times 10 to the 4 to 1.5 times 10 to the 4. That is 15,000, between 10 and 15,000. So conservatively, it could be any of these two values. Between 10, it could be 11, 12, 13, 14, up until 15,000 watt per square meter Kelvin. The film coefficient for steam. So to be conservative, these books stuck around with, I believe, 10,000. Yeah, it just consider 10,000. The overall heat transfer coefficient can be estimated from equation 14.4a, which is this equation. But in practical terms, it will be this equation like you see there, which is 1 divided by the overall heat internal because it is an I in there, internal heat transfer coefficient that is equal to 1 over the tube, the film coefficient of the inside of the tube, that is HI, plus 1 over the fouling coefficient inside of the tubes, which is 5,000, plus this ratio, which takes into account the conduction. This is a conduction term through the tube wall. That's why you have the ratio, logarithm, natural log of the ratio of the outside diameter of the tube to the inside diameter of the tube, divided by 2 times the thermal conductivity at the wall, which is usually steel, steel or stainless steel, plus the ratio of the internal to external diameter of the tube, and also divide by this is the fouling coefficient on the outside of the tubes. This in this case is steam. What is missing in here, like you see here, not available, Na, is the fouling coefficient for steam. So the fouling coefficient for steam was not considered. So this term was just not considered, was ignored. That's why you see this term is this term is this term will represent this. So the areas in terms of diameters, right there. This term will represent this. And this term, the last term, is just ignored. 1, 2, 3, 4, 5. 5 terms, but we only have 4. So that you know that this term, that the fouling coefficient, that includes the fouling coefficient for steam, was ignored. Okay, for this particular case, and it makes sense because steam is boiled from soft water, so it produces no deposition. And in real life, it's just like that. Okay, so solving for this will be 1 over 1650 plus 1 over 5,000 plus this, we know the numbers. The outside diameter was 0.019, the inside diameter was 0.015, 2 times Anderson, 2 times the thermal conductivity, which was 45, and then plus the last term. The last term was internal to external diameter, and then the outside film transfer coefficient for steam, which was taking us 10,000 from table 14.4, which we saw with you guys So this term 1 over 1650 is this value, 1 over 5,000 is this value. Doing this calculation of numerator divided by the denominator in here came out to be 0.00004. And the very last term, which is 0.015 over 0.019 and divided by 10,000 came out to be 0.00008. The units in here, as you see in there, are meters squared per Kelvin over watts. So this is inverted. That's why you see 1 over U, the overall heat transfer coefficient for the internal, overall internal heat transfer coefficient. So adding all these terms, they sum up to 0.00093 square meter Kelvin per watt. So now we can check the assumption that was made. What is the percentage delta T, the change in temperature, across the ethanol film? So if this is the term accounting for the 1 over the film coefficient of ethanol, so this magnitude divided by the total will give us the delta T across the ethanol film times 100. It came out to be 65.6, which is close to 66 of the total delta T. And the percentage delta T across the steam film will be taken from the last term, because the last term accounts for the film coefficient of steam, which was 0.00008 divided by 0.00093, which was a total of 1 over mu, 1 over u, I'm sorry, 1 over an internal u. The total was 0.0093, so we divide this term by this term. It came out and times 100, it came out to be 8.6%. So previously, it was assumed that 10% of the total delta T, the steam was responsible for only 10% of the total increase in delta T, while the delta T across the ethanol film was mostly responsible for the increase in the total delta T, and this seems to be true. That is, 70% was previously assumed, as you see in there, and 10% for steam was previously assumed. And we doing the check on the assumption, 65.6% seems to be responsible for delta T increase of ethanol, and 8.6%, almost 9%, responsible for the delta T. The steam was responsible for the total increase in delta T. So that seems to be, so the assumption previously made, they were not too far from the truth. The delta T assumptions are sufficiently adequate to proceed. In the determination of the pressure drop due to friction in a new tube or pipe, assume U is constant over the length of the exchanger. This is a simple way to assume this, particularly for horizontal exchangers. We could see that at least the literature mentions that when you have an evaporator, you have a vertical exchange. So the tubes are vertical and fluid is evaporating along the length of the tubes, then U will not be constant along the length of the tube. But since we only have not latent heat, but we only have sensible heat in here, there is an increase in temperature of the fluid, but no phase change, then this assumption that U is constant over the length of the exchanger is a correct assumption. So once again, once we have the total of 1 over U in square meter Kelvin per watt, we invert this to get watt per square meter Kelvin, and then we obtain the overall heat transfer coefficient between ethanol and steam. And also to determine the delta T logarithmic mean, there is a formula for that. You guys might be aware of that because this is material from fundamentals of heat transfer. So that will be 110, which is the temperature of steam, minus the incoming temperature of ethanol, minus 110, which is the same temperature as steam. Steam condenses at the same temperature, so it does not change in temperature, minus 65, the exit temperature of ethanol. And then over the logarithmic mean of the both differences, of this difference over this difference, it comes up to be 66.9. It will be delta T logarithmic mean. So from equation 14.6, you guys might be aware of this equation. You might remember this equation, Q is equal to M CP delta T, but also Q is equal to UA delta T. So when Q is equal to MCP delta T, and we have all these values, we know CP, we know delta T. This is from the ethanol side, the cold side. That's what you see, the cold side. Why is it cold? Because it was heated from 15 to 65, so it came in cold. It came in at 15, so it was a cold fluid, while steam was a hot fluid because it already came at 110 and it condensed. It gave up heat, but it condensed at the same temperature. So ethanol is a cold fluid. That's what you see MCP delta T. This is a calculation done for the cold fluid. 9 kilograms per second is the mass flow rate of the cold fluid. Right. CP is the heat capacity of the cold fluid and the delta T of the cold fluid. So the heat load, the required heat to heat up an ethanol, let's say pure ethanol fluid from 15 to 65, flowing at 9 kilograms per second. That heat load will be 1.17 times 10 to the 6 watt, or 1.17 megawatts. So it is a lot of energy. This could also be expressed as 1,170 kilowatts, which is a lot of energy required to heat this up, because the flow, 9 kilograms per 1 second, is a very high flow. I mean, this requires a lot of energy to heat this up. So what is the area required to heat this up? So we know that Q is also equal to UA delta T. You guys might be, once again, familiar with this from fundamentals of heat transfer. So solving for there and knowing that Q is the same as this Q, because energy is conserved, is the same Q. We solve for A, the internal area, the required area for heat transfer, would be Q over U delta T logarithmic mean. And U was recently calculated as 1,075 watt per square meter Kelvin. Delta T logarithmic mean was 66.9. So replacing both values and the Q from the previous calculation for the cold fluid came up to be 16.3 square meters. Now, what would be the length of the tubes? If we have already been given the amount of tubes, they told us 50 tubes per pass. You guys remember from the problem statement. Problem statement mentioned the exchanger, or the heat exchanger, will be the same, contains a total of 100 tubes, 50 tubes per pass. The ratio, and they also mentioned that the ratio of the total inside to cross-sectional area per pass to header cross-sectional area per pass can be assumed to be 0.5. That is, the header has twice the area than all the area of inside of the tubes. That's pretty much what we're seeing in here. That's what this means. Very good. So there are 100 tubes, 50 tubes per pass. Okay, so to determine the area, and from the area, we want to determine the length of the tube, knowing the amount of tubes. So we have the area by the amount of tubes, the total number of tubes, divided by this number, which came from, once again, the wetted area, which is pi times V, that is VI, which is the internal diameter of the tube. What tube is this? It's a 3/4 of an inch BWG 14 tube. It has an inside diameter of 0.015 meters, or 14.8 millimeters, or something like we saw in table. That is 20.8 from the book of Turton. Okay, so we divide square meters. Remember, these square meters divided by the number of tubes. This has no area, just a number of tubes. Divided by this, which is 5 times this is in meters, in linear meters. So we divide square meters by meters, we're going to get the length in linear meters. It comes out to be 3.47. So the length of the tubes in this particular exchange should be at least 2.47. We can round this up to 2.5 meters, having 50 tubes in one direction and a front header, a back header, just like we saw last Tuesday. And then the return, in the return direction, in the opposite direction, another 50 tubes in the lower half of the exchanger, coming from the back header to the front header. Okay, so that would be pretty much the mechanical, approximate the mechanical assembly of this exchanger. Now, to obtain the pressure drop, so far so good. To obtain the pressure drop, hopefully we finish this, and then we see the Excel file, how to put this in Excel. And it's actually very interesting how to calculate this and put this into Excel, so you guys can have the practice to do this. Because in real life, you might throw in some numbers in paper. I do that myself. And then you want to express that in Excel just to check yourself your numbers are correct. Okay, so to obtain the pressure drop inside the tube, use equation 1423, which is this equation, and equations 1423V, just like you see there, and 1423B, just like you see there, to evaluate a beta sub I, which is this factor, and F sub I, the defining friction factor for this case, which has this correlation. Why these particular equations? Like, why do we have to use equation 1423B? Well, the main reason is that when the Reynolds number was calculated, it came out to be 16,950. That is, it was way above 2,100. Like you see, that's about the limit between fully developed turbulent flow and laminar flow. You guys might remember that the number is 2,100 for above 2,100 considered in a turbulent flow region in a circular pipe. When it's a plate, it's 10 to the 5th. You guys might remember that when it's a flat plate. But inside of the tube is 2,100. So 16,950 is way over 2,100. So this is a turbulent region. That's why we have to use the defining friction factor for this case when the Reynolds number is above 2,100. So this is a correct correlation. And 1423D, because equation for delta P inside of the tubes is in terms of beta. Beta is in terms of K sub L or K sub 1, whichever this is, seems to be K sub L, and P, the number of passes, delta T, of the fluid inside of the tubes, the ratio of the viscosity inside of the tubes to viscosity of the wall to the power of 0.28 divided by the temperature coming in, the temperature leaving the exchanger, times the Prandtl number inside of the tubes to the power of 2 divided by 3. Pretty much that's what it is. So to evaluate beta sub I, we have 1 plus, yeah, there you go. Just this equation, 1 plus 0.51 times K, the same equation, where K sub L is equal to 1 minus the ratio of the area inside of the tubes, the total area inside of the tubes to the total area of the headers, squared, plus K sub C, plus 0.5 times number of passes minus 1 divided by number of passes. That is the number of passes in the exchanger. In our case, we have 2 passes. So that will be 2 minus 1 is 1 divided by 2. Pretty much that's what it will be. Okay. Now to calculate, Alexander. Now to calculate K sub C, so we have our formula. Where is this formula came from? Well, if we check in here, this is from table 12.1, which is again from Peters. And this equation is considering a sudden constriction. Remember, when you have an exchanger that has a front header, then they have the tubes from, let's say, the tubes that are welded on a steel plate. And the tubes, they are connected to a plate on the other side of the exchanger, where the back header is all, is all bolted. It's actually bolted because you can take the bolts out and you can clean it, but it is bolted. So, but you have, when the fluid comes into the header, it has this big area, empty area, and it comes inside of the tube, then it's a constriction. El flujo pasa por el intercambiador, por el cabezal frontal, y luego que tiene un área pues bastante grande, un área libre bastante grande, y luego el flujo es, aquí le dicen, tiene una constricción, esa viene a ser la palabra. Y usted puede observar aquí, viene de un área grande y se mete en un tubo, en un área bastante pequeñita, hay bastantes tubos, hay 100 tubos, 50 en un sentido, 50 en el sentido, el flujo lo tiene que constrictar, si se puede decir así. Hay que tomar en cuenta esa constricción, que es lo que hace esta ecuación. Okay, so we have a constriction from the big area to the small area. When that constriction is less than 0.715, which is our case, because it says in our problem that the constriction, and that's what we saw in here, was 0.5. We saw that here, the statement of the problem. It says the ratio of the total inside tube cross-sectional area per pass to the header cross-sectional area per pass, SI to SH, can be assumed to be 0.5. So when we check this table from Peters, and we see that for a sudden constriction, es decir, una constricción repentina, that's what sudden means, una constricción repentina. Y eso es lo que ocurre en intercambiador. Entra el fluido en el cabezal y se constricta, se reduce repentinamente, pasa a estar del cabezal al interior de los tubos. Es una cosa inmediata, ¿no? Porque el flujo es forzado, es forzado por una bomba, ¿no? Entonces, dice aquí, de A2 a A1 es menor cuando este es el caso K sub C de la K de la constricción, básicamente es lo que es igual a esta expresión que se encuentra aquí. Punto 4 por 1.25 menos A2 sobre A1 y se lo considero así. K de constricción es igual a 0.4 por 1.25 menos SI sobre SH y es lo que obtenemos aquí, punto 3. Okay, so now KL, which is this value, we know this ratio. Now we know KC, and 0.5 times the number of passes, which is 2 minus 1 divided by 2. Then we can solve KL, which we can use in this equation to get beta sub I. So KL, as you see, there is 1 minus 0.5 plus 0.3. This 0.3 was obtained right there from KC, K of the constriction, according to this relationship from table 12.1 from Peters. And then the last term in the KL equation, 0.5 times 2 minus 1, number of passes, divided by 2 is 0.8. Finding friction factor for fully developed turbulent flow, 0.0446 times the Reynolds number to the negative 0.2. Por favor, tome en cuenta las fórmulas que usted vaya a recibir, porque le vamos a incluir todas las fórmulas que usted necesite. Hay ocasiones, como en este caso, que el factor de fricción de Fanning está un signo negativo. Me en cuenta eso cuando usted eleva la potencia, no se olvide de ponerle cuidado a los signos de las potencias, no va a ser que obtenga un valor completamente diferente al valor que debería obtener, ¿no? Entonces ahí el resultado final va a estar bastante errado. Entonces, en este caso es a la potencia menos 0.2. Reynolds number que fue previamente obtenido 16.950 a la menos 0.2 por 0.046, que es la constante de este factor de fricción en Fanning para flujo turbulento y se obtuvo 0.0066. Finalmente, beta sub I. Beta sub I, according to these equations, 1 plus all these term in the numerator divided by all these in the denominator. We can check in here. It's 0.51 times KL. KL came out to be 0.8 times number of passes, which is 2. That's why you see 2 times delta T F sub I. Let's see. This is delta T in F, delta T of the flow internal, that is inside of the tubes, 110, the hot temperature, minus, once again, this is the bulk average temperature. 15 plus 65 divided by 2 is 40. So the difference between the hot fluid and the bulk average temperature of the cold fluid, that will be delta TFI. Now the ratio of viscosities to the power of 0.28. Here, ratio of viscosities was previously calculated. Where is that? It was in here. We explained this already, 0.0009 divided by 0.0004. So it's 2.25. We can add to be 2.25 right there to the power of 0.28. What is also included in this equation, beta I, is, we will see here, Fi has been included. Where is Fi? And we see right there, this Fi, the final friction factor, was included in this equation. And it's a bit strange because the final friction factor is not here. I don't see the final friction factor there. And I don't see the final friction factor there. But the final friction factor is right there. So beta can be calculated with the previous values that we have. And then to calculate delta PI, then we need to calculate the final friction factor. And it was already included in here. So what is this value represents? This value represented the friction factor. What is the friction factor? There, 0.0066. That will be the friction factor of one tube times 100 tubes, because there are 100 tubes per pass. That would mean 0.656, which is the number that you see there. And that is divided by the difference in temperature in and out times the Prandtl number to the 2/3. Prandtl number was calculated 14.32 to the 2/3, and the difference in the temperatures of incoming and exit temperature of the fluid. So this came out to be 1.16. Once again, now using using delta PI, we could replace the numbers. You see the delta P for inside of the tubes is using beta, is using final friction factor, is using G, is using the length, is using number of passes, is using rho, the density is using internal diameter, is using phi. For fully developed turbulent flow, phi is this relationship, which is 2.25 to the 0.14 times 1.02. And you also see that the final friction factor, 0.066, has been taken as it is for one tube, like you see right there. Final friction factor for one tube, while beta included the final friction factor for all of the tubes. For some reason, they did that. Although I have to recognize it is not in the original formula. It's not in the original. So in a case, we have to calculate this. My recommendation, you guys don't have to worry about the final friction factor in this equation, beta sub I, because it's just not in the formula. But for delta PI, you do have to include it and consider the final friction factor for 1, 2, as you see right there. Okay, so this came out to be 8,169. Yeah, these two more slides, and then I'll show the Excel file, and then we pretty much are done with this. It says, using Kern's method for the tube side fluid, the standard term for the frictional pressure drop in circular tubes can be used the addition of 4 velocity heads per return due to changes in fluid direction for multiple tube passes. The recommended equation is delta T of the fluid inside of the tubes. This is the expression, which is 20.77. This is true. Lo que estamos haciendo, esto acabamos de ver, es la fórmula recomendada del libro de Peters. Mire usted que los autores tienen diferentes criterios. Y los autores se acogen a diferentes fórmulas. Perdón. Se acogen a diferentes fórmulas. En este caso, Peters se acogió a la fórmula 1423 para describir la caída de presión al interior de los tubos. Sin embargo, volviendo al libro de Turton, que ahora usted ve aquí, en la ecuación 2077 es el capítulo 20 del libro de Turton versus el capítulo 14 del libro de Peters que acabamos de ver. Más bien, Turton es del criterio de que la fórmula debería ser la que usted ve expresada ahí, donde aquí él sí considera también el factor de fricción de Fanning, pero no lo considera como lo habíamos visto nosotros simplemente con esta relación de 0.046 por el número de Reynolds a la menos 0.2. Él considera el factor de fricción de Fanning como la ecuación 1916 que habíamos visto nosotros cuando estuvimos compartiendo acerca de tuberías, bombas y compresores, desde el capítulo 19 de Turton. Mire, la ecuación es bastante más compleja. No extremadamente compleja, sino un poco más compleja que la ecuación que observamos aquí de Peters. Criterio de diferentes autores. Eso es lo que ocurre. Pero bueno, lo que hemos hecho aquí, esto no nos pide, lo que hemos hecho aquí es realizamos el cálculo en Excel para Peters y realizamos el cálculo en Excel según la fórmula de Turton para ver qué tan diferentes estaban las dos. Y usted se va a sorprender un poco. Nos dice aquí, the recommended equation, estas son las ecuaciones, para la caída de presión dentro del tubo y para determinar el factor de fricción en Fanning en un fluido donde está completamente desarrollado el régimen turbulento. Esta es la ecuación. De otro modo sería la ecuación, usted recordará de Hagen-Poiseuille, que es 16 sobre el número de Reynolds. Esa estaría quizá un poquito más cercana. Un poco, pero no tanto, porque el coeficiente sería diferente. Bueno, nos dice, where NTP is the number of tube passes, UI is the velocity inside of the tubes, DI is the internal tube diameter. In equation 2077, the first term on the right-hand side accounts for the frictional pressure drop in the tube, que es este de aquí, and the second term accounts for the losses occurring at the ends of the exchanger where the fluid changes direction. Está tomando en cuenta la caída de presión dentro de los tubos, este término, y este otro término está tomando en cuenta las pérdidas que ocurren al final del intercambio, en el lado del, cuando llega al cabezal y da la vuelta, hay ciertas pérdidas también. Pérdidas en presión se refiere, eso se refiere con pérdidas. Applying equation 2077 and 1916, que son estas dos, to the previous pressure drop calculation using Excel, we obtain Fanning friction factor 0.0063. Comparemos esto con 0.00. Ahí estuvo. Mire usted, interesante que el factor de fricción de Fanning con esta correlación sencilla nos dio un valor bastante cercano al calculado con esta otra ecuación, que se la ve un poco más compleja, ¿no? Sin embargo, la caída de presión aquí dio aproximadamente 10.290 versus los 8.169. Para terminar, revisemos por favor la hoja de Excel que contiene, estos cálculos y ya me despido de ustedes si lo dejo bien. Vamos a ver si está aquí. Acá está. Ecuación, ejemplo 14.3, usted puede ver del lado del vapor, espero que ustedes todos, vamos a ver si lo agrandamos un poquito, todos pueden ver esto. Del lado del vapor, del lado del etanol, que dijimos entró a 15, salió a 65, el delta T general. Estos parámetros para ese valor promedio, el espesor de la pared, esos son dimensiones de la tubería 14 BWG, 3/4 de pulgada, el área de sección transversal, el área es el perímetro húmedo, ¿no? Metro cuadrado por metro de longitud de la tubería, la velocidad, el factor GI, que es el flujo másico dividido para el área de la sección transversal, el número de Reynolds, el número de Prandtl, esos son valores calculados, usted los podrá ver ahí. Estos son calculados, ¿no? Número de Reynolds, el número de Prandtl, este valor estimado 89, como lo vimos en el ejemplo. La relación de la viscosidad del promedio del fluido a la viscosidad en la pared. HI, el coeficiente interior de transferencia de calor. Mire que fue determinado a través, y este se determinó con la ecuación de la correlación de Sider-Tate, y eso es lo que usted ve aquí. Todos estos cálculos usted puede ver. D92 a la 0.8, que es el número de Reynolds a la 0.8. D93 a 1/3 es el número de Prandtl a 1/3. D95 al 0.14 es la relación de viscosidades a la 0.14. D81 por 1000. De 81 viene a ser Esto es el conductividad térmica seguramente para ponerle en joules sobre el metro, Kelvin y segundo, para que las unidades pues todas finalmente se cancelen. Se obtiene 1644, este valor de la tabla, 14.3, si recuerdo bien, este valor de la tabla, 14.4, es el coeficiente de película externo para el vapor, que vimos 10.000, el fouling factor, el factor de deposición para el vapor, lo ignoramos, como recordará usted, 1 sobre el coeficiente global de transferencia de calor, pues tomando en cuenta estos factores, y usted ve que se tomó en cuenta también el segundo término que toma en cuenta la conducción de calor, ¿no? La resistencia a la conducción. Delta T medio logarítmico calculado también. Esto pues son, digamos, ¿qué habré hecho aquí? El Q, que es la carga total de intercambio de calor, era 1.167, esto es en megajoules por segundo, megawatts, megawatts térmicos. El área salió en 16.3. La longitud 3.44, creo que al autor le dio 3.70 y pico, pero bueno, me dio 3.44. Mire usted la caída de presión. La caída de presión usando la ecuación K sub L, F sub L, este es 0.046 número de Reynolds por menos 0.2, mire usted aquí está el menos, hay que tomar en cuenta eso. Efectivamente dio 0.00656. Beta, que se encuentra aquí, 1.16, algo similar a lo que dio el autor. El delta P, 8000, con la fórmula 14.3, si recuerdo bien, de Peters. Ahora, usando el método de Kern recomendado por Turto, tuvimos esa esa constante de rugosidad para tubos de acero comercial, es un valor conocido, por eso es una constante, por eso ve aquí no hay cálculos. El primer término de el cálculo del factor de fricción, porque el factor de fricción, de acuerdo a la ecuación de Pavlov, tiene dos términos. Entonces, el primer término es S, el segundo término es S, y finalmente el factor de fricción de Pavlov, ¿no? Para un flujo en régimen completamente turbulento. Y el delta P de la ecuación creo que era 2018 y nos arrojó 10.000. Es decir, aquí tenemos nosotros un diferencial, no sé, estos otros números. En algún momento estuve haciendo cálculos de no sé qué, donde parecía otro número. En el momento no recuerdo, porque a veces uso la misma hoja de Excel y me pongo a hacer cálculos de otros ejercicios. Entonces ve usted un diferencial, digamos, importante, ¿no? Entre estos dos, pero un diferencial que son, yo creo que ya sé. Esta dividido para 101.325, que es un bar, es una atmósfera de presión, ¿no? Representa una caída de presión de 0.08 atmósferas aproximadamente. Eso creo que es eso. Y este de aquí dividido para los mismos 101.325 representa una caída de presión de 0.1 atmósferas. Es decir, entre 0.08 y 0.1 atmósferas la diferencia es, entre estos dos pareciera que fuera importante, pero realmente la diferencia es pequeña. Es decir, pudiéramos en teoría usar cualquiera de ambas relaciones y obtener un valor que estaría bastante sensato. Jóvenes, muchas gracias por su tiempo. Me he pasado 8 minutos, 9 minutos, no quiero tomar más tiempo del tiempo de Fernando. Nos vemos, Dios mediante, tienen tarea, por favor no se olviden, nos vemos Dios mediante el martes y nos vamos de cabeza. Pido su paciencia el día martes, nos vamos a extender un poco de antemano en la conversación para que cene usted antes de la clase, nos vamos a extender un poco, tenemos que cubrir en 2 clases separaciones, porque no tuvimos una clase debido al feriado. Por lo demás, jóvenes, les deseo un excelente fin de semana a cada uno de ustedes. Tengan un buen descanso, un buen tiempo para trabajar, estudiar, en fin, y nos vemos, si Dios permite, el martes. Okay, buen fin de semana, cada uno de ustedes.
Gracias, profe.
Hasta luego.
Gracias.